Alright gang, here we go. This is Chem 2, Unit 6. We're talking about enthalpies of formation. Okay, so we've talked lots about enthalpies. We just finished talking about Hess's Law. Today we're going to take the idea of Hess's Law and specifically apply it in a very useful way. Alright, but first we need to identify what this thing is called delta HF, or enthalpy of formation. It's essentially defined as the enthalpy change for a reaction in which you make the given compound from its constituent elements in their elemental forms. Okay, so this is important. Constituent elements in their elemental forms. Okay, so that's known as the enthalpy of formation. All right, the change in enthalpy to make that thing if you started from the basic elements in their elemental form of whatever that thing is made of. All right. So that's known as the enthalpy of formation, and specifically we have another idea of that called the standard enthalpy of formation, and that's where we've got this little degree symbol up here. This means standard. Okay, all right. So the standard enthalpy of formation, and these are the enthalpies of formations when they're measured under standard conditions. And remember, standard conditions is 25 degrees Celsius and 1.00 atmospheres. All right, so enthalpy of formation and then standard enthalpy of formation. The standard just means you're at standard conditions. Here's a whole bunch of them. All right. Notice some of them are exothermic, some of them are endothermic, some of them are very large, some of them are very small. Okay, they kind of vary. Exothermic, endothermic, etc. All right. So when you're writing, okay, we're just going to look at this one here. When you're writing enthalpies of formation, okay, you still need your delta H. So it says the heat of formation of water liquid is negative 286 kilojoules per mole. Okay, what is the correct thermochemical equations? All right, so for the delta H of formation. All right, so remember we're making one waters, okay, and it's always from its elemental components in their elemental form. Okay, so that means hydrogen and oxygen. So hydrogen is diatomic, so it should come from an H2, and oxygen is diatomic as well. So it should come from O2. All right, so any of these that formed it from non-diatomic hydrogen and oxygen are right out. So the hydrogen's gone. That one might be right, that one might be right, that one's wrong. Okay, and then we're not forming this, we're reacting this, so that one's wrong. So we're down between B and C is the correct answers. All right, now it says that it's in kilojoules per mole. Okay, all right, so the only correct answer, okay, would have to be this guy here. Okay, and that's because we're forming one of these water, and we want to know the enthalpy of formation of this, and that's always given for 1 mole of whatever it is you're talking about, not 2 moles. So 1 mole. So H2 plus 1/2 O2 yields H2O. So notice that we've got that 1/2, breaking that rule. Okay, the rule, sneezing trees. Okay, so calculation of delta H. So we've talked about several different ways of calculating delta H. In the past, we've done calorimetry, we've talked about Hess's Law. So let's talk about delta H of formation. So let's assume, so this is just combustion reaction of propane, right? C3H8. 5, and we get this guy here. Okay, so imagine that this is going on, right? So this is, instead of it just combusting, blowing up, blah, 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 we're going to imagine that this occurred in 3 steps. And remember, Hess's Law says that if we can break up our reaction into individual steps, we can add up the delta H for each of those individual steps, and we can get an idea of what the delta H is for the overall reaction simply by adding them up. Okay, so let's do the same idea, but instead we're going to do it based on we're going to use enthalpies of formation. Okay, so first, if we decomposed propane into its elements, elements in their elemental form. Excuse me. So we've got methane forming carbon and hydrogen. Okay, and carbon elemental form is graphite. Okay, all right. So that's the first step. All right. So we've got that guy going on, breaking down our propane into those 2 guys there. All right. And then we'll form CO2. So we'll take that carbon and that oxygen, and we don't have to break down oxygen here because oxygen's already elemental O2. Okay, so we can combine those 2, and those would form our CO2. Okay, and then the last step would be combining the hydrogen from breaking down the propane with the oxygen to form the water. Okay, so we took our C3H8, broke it down, and then formed CO2 and H2O. And this is essentially what we have. So this is our reactants. This is what we started with. Okay, and we broke them down into their elemental forms. O2 is already elemental, so all we had to do was break down our carbon and hydrogen. We formed our carbon, got our hydrogen, and then we start putting things together. First step is we combined our CO2, our carbon and our oxygens to form CO2. Now notice that to break up C3H8, it was an endothermic reaction. It took it 103.85 kilojoules to make this occur. Now it's an exothermic reaction forming the CO2, okay, and then it's an exothermic reaction again forming our O2. Okay, and notice that we've got this full cycle here, and then this, if we take each of these three and add them up, 103 minus 1181 minus 1143, we'd have the total delta H of reaction of this guy here that we'd find if we used like bomb calorimetry or something like that. Okay. So these would be all of the steps, right? So we've got this reaction here where they break up, and we could see we could Hess's law this sucker, add them all up, right? Okay, we could add up all these guys. Our carbons would cancel reactants and products. Okay, our oxygens would add up to be 5. Our hydrogens would cancel. We got 4 here and 4 here, and then we'd left with C3H8 plus 5O2 yields 3CO2 and 4H2O, exactly what we expected, right? So that's what this guy's right here. So then we can just take our Hess's law and add up the delta H reactions for each of these 3 steps. Okay. Now this is the wild part. Like you'd be like, oh great, it's another application of Hess's law. Now the neat thing with this is that we can use this idea and we can apply it to any reaction where we have any reaction. As long as we have the enthalpies of formations for each of those individual, whatever it is, things, the elements, compounds that we're talking about in our reaction, then we can just use this formula. Okay, where we just take our delta H of formation of the products minus the delta H of formation of the reactants. Okay, the only caveat here is we need to multiply them by their stoichiometric coefficients. So you need the balanced chemical equation with their stoichiometries. Okay, multiply each of the individual products and reactants by their stoichiometry, add up the products, add up the reactants, and subtract them, and you're done. Okay, and you can find the delta H of your reaction. All right, so same idea here. They've done the same thing here, okay, but instead of going through Hess's law, now we're going to calculate it with our delta H of formation of each of these. And so we can use the values from the appendix in the book where we have the delta H of formation, and you'll find those in the appendix in our textbook. All right, so it's products minus reactants, so they took 3 times the delta H of formation of the CO2, okay, and they added that to 4 times the delta H of formation of H2O. Okay, and then they're going to subtract out 1 times the delta H of formation of C3H8, okay, and then add that to 5 times the delta H of formation of O2, okay, and that's all we've got right here, right? So CO2 is 393.5, water's this, etc., etc. And then they just walk through the math, and then we find, again, there's our delta H formation. Notice that it's exactly the same number as this guy here. All right, it's just more sig figs because we had more sig figs to work with our delta H formation. All right, so we'll do practice one of these real quick. All right. So here we've got calculate the enthalpy change for this reaction. We're taking hydrogen peroxide forming H2O and O2. All right, and so we're going to take the delta H formation in order to find the enthalpy change for this reaction using this information. Okay, so products minus reactions, so our delta H, okay, of our reaction would be equal to, all right, and these are all standards, so we can assume that this is the standard enthalpy change for the reaction as well. So it's the sum of the products, okay, minus the sum of the reactants, okay. All right, so the products, well, that's H2O and O2, okay, so the products, so that would be 2 times the delta H formation, okay, delta H of formation of H2O, okay, plus the delta 1 times the delta H of formation of O2. All right, so those are our products, and then we'll subtract out our reactants. Well, there's only one reactant, so that makes it nice. So it'd be 2 times the delta H of formation. Okay, delta H, I forgot the delta H standard formation of H2O2. Okay. All right, so delta H formation of water, it would be 2 times our water value is negative 285, negative 285.8, okay, and then we're going to, water, oxygen 0, so we'll just ignore that guy, minus 2 times delta H of formation of hydrogen peroxide, which is negative 187.8, okay. We'll plug that into our calculator, say 2 times negative 285.8 plus 2 times 187.8 Okay, and we get negative 196 kilojoules. Pretty easy. All right. We do the next one, but I don't have a textbook with me, so we'll do it in class. All right. Calculate the enthalpy of formation using an enthalpy of reaction. All right. So I just wanted to do this real quick, this first one. Okay, it says given this equation here, it says given 2SO2 plus O2 yields 2SO3, which of the following equations is correct? So essentially what they're doing is, say you do products minus reactants, but they want you to think about what's going on here. And we want to figure out what is the delta H of formation of the SO3. So now we're going to be working a little bit backwards from what we did before. Okay, so they give us, we're going to assume that we have the delta H of the reaction, okay, but we want to figure out the delta H of formation of SO3. Well, remember, the delta H of the reaction is equal to the delta H of the products, okay, minus the delta H of the reactants, okay. Okay, so in this case, we only have one product. That's nice, so that's our SO3. Okay, so essentially what we're going to get is well, if we're going to rearrange this, we want to find the delta H of the product. Well, we only have one, so we don't have to worry about adding it. So that makes it nice. So we'll have delta H of our product, okay, is going to be equal to, so if we added this over, well, that's probably the easy way to do it, isn't it? Delta H of our reaction, okay, plus the sum of the delta H of our reactants. Okay. Not only that, but we can see that this guy's going to be 0 anyway, so essentially this sum goes away as well. That makes it nice too. So they've helped us out in two ways. So it'd be delta H of our products, okay, is equal to the delta H of the reaction plus the delta H of the reactants. Right? Okay, so now we just have to worry about plugging these guys in. Well, the delta H of the products, so that'd be 2 times the delta H of formation of SO3, which is what we're after, okay, is equal to the delta H of reaction. Well, we can't replace that with anything, so that'd be just delta H of the reaction, plus the delta H of the reactants. Well, we only have the one reactant we care about, so that'd be the 2 times the delta H of formation of SO2, okay. So does that match one of the ones here? So 2, so both these guys are just one of those, so that's no good. And then 2HFSO3, okay. Delta H of the reaction, okay. Well, this one's right out because it's got a negative sign, so is this one. So does this one match here? So 2HFSO2, so it's got to be C, all right. And then this one here, we'll do this reaction in class. Oops, we'll do this one in class as well, okay, because we need those tables of information. I forgot the textbook at school. But anyway, so good luck with your text problems. Let me know if you have any questions. This stuff's not too hard. Products minus reactions, just remember to multiply them by your coefficients. Make sure you balance it to start. Other than that, it's pretty easy. All right, I'll see you on the flip side.